Horrible. All right, ladies, go ahead and take out your devices. We're going to do pair deck today. I want you guys to answer some questions in the PowerPoint that we've already gone over. So take out your devices and then log in, okay? The code is on the board here. All right, so there's the code on the board, KGABP. If you guys can't see, I'm going to write it really quickly on the side. Go ahead, joinpd.com and enter the code. And then right when you enter the code, it takes you to this slide right here. It should take you to this slide. Define chemical bond, list the 3 types of bonds, and what is the difference between ions and a polyatomic ion, okay? So if you can't see it on the screen, you can see it on your device. Answer those questions. This is your do now. This is the beginning. I'm gonna give you about 5 to 10 minutes on this, okay? You can use your notes. Try your best to put these definitions in your own words, because it's easy to copy and paste, but if you put it in your own words, you're processing it. And then it's a little bit easier for you to remember. So try to put it in your own words. It'll help you remember. I'm gonna give you 3 more minutes. 1 more minute, okay? Finish it up. Okay. Start wrapping it up. All right, so let's see what some of you guys have written. Okay. So, chemical bond is when electrons come together and form a strong pair. Good. A type of force that holds 2 or more atoms together. Good. An attraction between positive nucleus and negative valence electrons. Perfect. I love that this person included that it's the valence electrons that are involved in a chemical bond. If you don't have that in your notes for a chemical bond, that valence electrons are the ones involved in the bonds, make sure you write that down, okay? Yep, a force that holds 2 or more together, 2 or more atoms together. Good. All right, the second question. The second question was the 3 types of bonds. Can somebody tell me, just raise your hand really quickly, what are the 3 types of bonds? Andrea?
Ionic bonds, covalent bonds, and metallic bonds.
Good. Ionic, covalent, and metallic. We've been drawing Lewis dot structures for ionic and covalent, so these you should know off the top of your head, okay? You know it by heart. And then the last question, what's the difference between an ion and a polyatomic ion? Let's see what people wrote. Ions are atoms that lose or gain electrons. Perfect. There's more to it though. Tell me what a polyatomic ion is. Ions between metal and non-metal, that's ionic bond. Close though. Polyatomic ions are composed of 2 or more atoms. Yes, they are. What else? Polyatomic, 2 or more atoms. Poly has multiple. Let's see. Ions and ions gain or lose electrons to become stable. Polyatomic ions are ions composed of 2 or more atoms. Yeah. Make sure that you note that they have 2 or more atoms, but together they act as one group and they have a charge all together. Okay? Cool. All right. Any questions so far? All right. I'm going to show you guys what we're doing today. All right. So I know you can't really see this all that well, but here's what we're focusing on today. Today we're going to be talking about the formation of ionic covalent bonds using Lewis dot structures. We've been practicing this over and over, but we need more practice, okay? We are going to move on with Lewis dot structures as well, and we're actually going to start predicting the shape of molecules using Vesper theory. And then we're going to talk about the domains, right? The domains are the electron pairs. So you started with the do now. We're going to review our homework. We're going to go over the answers, so make sure you have your homework out. Next, I'm just gonna review really quickly Lewis dot and Vesper. We're gonna do an activity and then you're gonna get started on your homework, okay? Cool? Yes. All right. Both answer keys are on Schoology. Go ahead to Schoology, but here is the first one, ionic and covalent bonding. Here's the answer key on the board, all right? For the first 2, I have them on the board here. The first 2 are both ionic. I'm gonna zoom in to what happens to those actual atoms and their electrons, okay? They're both ionic. Only the top 2 were ionic. Everything else was covalent. So here we go. For the first one, sodium has 1 valence electron, chlorine has 7. For ionic, I have to make sure that I do what when I'm drawing the Lewis dot structure for ionic? Go ahead, say it. Giving what?
Giving the atom.
Giving the atom, the whole atom? What am I giving? What is this dot? Yes. The valence electron I'm giving, so I have to draw an arrow. What else do I have to do at the end for ionic? What am I doing here, Bethany?
You have to show at the end of the brackets how much they gained or lost.
Good. So I put brackets, and then I show all the valence electrons, and then I put the charges, don't forget. So I only put 1, I gave 1 electron away to chlorine, which makes it +1. Chlorine gains that electron, -1. Cool? And then there's that one there. Magnesium gives away 2. 1 to each separate chlorine. Make sure you write chlorine twice. I don't want to see any of this. I saw a lot of this before in other classes. That's not correct. Why is this not correct? Miriam.
Because we could say that chlorine gained 2 electrons.
Exactly. This looks like it gained 2 electrons, but that's not right. In reality, this one gained 1 electron and another chlorine gained another electron. Okay? So I don't want you to combine both of these chlorines into one bracket. Don't do that. Keep it separate. Okay? I'm going to move on. Can I scroll down?
Yeah.
So here is bromine, covalently bonded to another bromine. I circled the 2 lonely little electrons, and that turned into a single bond. You could have done it the other way too. What's the other way with the math? What do I do for figuring out the Lewis dot by calculating electrons?
Valence electrons.
Yes, so bromine has how many valence electrons? Somebody raise your hand. How many valence electrons for bromine? Somebody, Leslie.
7.
7, and I have 2 bromines. So 14 electrons, valence electrons. How many pairs is that? 7 pairs, yeah. Okay. So then all I have to do is bromine, just immediately bond it, and then fill in the rest, okay? Let's see if that works out. So that's 1 pair, 2, 3, 4, 5, 6, 7 pairs. And do they each have 8?
Yes.
2, 4, 6, 8. Yep. 2, 4, 6, 8. Beautiful. Same thing this way. Check the rest. Let me know if you have questions. Somebody tell me why. Look right here for nitrogen. I have 3 bonds right here. So I call this a triple bond. But I also have 3 bonds right here. Why is this a single bond? Why did I classify that as a single bond versus a triple bond? Look at what's happening in there. What do you think? You want to go for it? Go for it, Jennifer. I promise I'll make you look good. Go for it.
Okay. It's single bond because the B is just doing with the F. It's not like it's doing with the same one. So like, I don't know.
So like it's bonded with this
yeah, with
F?
that one and the other, and it's just bonding the other ones.
Oh, so you're saying there's more than one F and
Yeah.
each of them have one bond? Versus what's going on here? Why is that different though?
Because that one's just it's bonding the same one, but like for the other one, she's bonding with different ones, so like that's why.
Perfect. Yeah. So she's saying that you have multiple Fs here, and each of them just have a single bond with each fluorine. This, it has 3 bonds with the same nitrogen. So if it's with the same atom, when it has multiple bonds with that same atom, that's triple. Look, same atom. They're all of these bonds are going to nitrogen. That's triple. This one right here, look, single bond over here, single bond over here. All the single bonds, all of this, okay. Single bonds, okay? Moving on. Okay, cool. So, like we just said before, so ionic bonding is in between a metal and a non-metal, okay? So, you have, your metal is giving away valence electrons. Your non-metal is receiving them, and then they create charged ions. Sodium has +1, chlorine has -1, and then they come together because of the attraction of their charges. Covalent is when they're sharing, okay? They all want to have a full valence shell, so they share electrons with each other. And that's between a non-metal and another non-metal. All right? And then we talked about metallic bonding, but metallic bonding is a little bit different, okay? You lose electrons. Metals lose electrons, and those electrons float around. It's like a sea of electrons. And then you have positive metals just hanging out too. So it really is just a bunch of electrons and cations floating around. So go ahead and answer this question on your screen. What kinds of atoms are involved in ionic bonds? What about covalent bonds? And then tell me what happens to electrons in all three types of bonds. Okay, so ionic is a metal and a non-metal, good. Covalent is non-metal and non-metal. So what's happening to their electrons? Looks like people are still writing that part. So what happens to the electrons in ionic? Somebody raise your hand. What happens to electrons in ionic? You know what? I'm use popsicle sticks. So get ready. Everybody better get ready. Unless someone wants to volunteer. You want to tell me, Leslie? All right. What happens to the electrons in ionic?
So in ionic, the electrons are given away to the other element.
Yes. So you have electrons that are given away and then electrons that are received. So it's transferring. What about covalent? What's happening to the electrons in covalent? Let's see. Jennifer, what happens to the electrons in covalent bonds? Okay. You have your notes up?
Yeah.
Okay. Somebody want to help her out? Look at your notes. Go to covalent bonds, you guys. It's in your notes. Haran, yeah.
Like it shares.
Yes, perfect. They share electrons. Beautiful. And then lastly, metallic. What's happening to the electrons? We just talked about this. Melanie.
They attract each other.
They attract.
Electrostatic.
That's a property of metallic bonding. Go ahead, Leslie.
It said that like metal is like floating around.
Yes, they're floating around with metals. Good. Okay, cool. All right, so moving on, you guys. So we talked about Lewis dot structures. We went through all of that. I want to go over Vesper theory, okay? So here's Vesper theory right here. Vesper theory stands for valence shell electron pair repulsion theory, okay? This is basically saying that atoms, or not atoms, molecules, take a specific shape. And the shape that they take depends on their domains, the number of domains that they have. And we said domains are going to be your pairs of electrons. They can either be bonds, like little lines, just like that, or they could be a lone pair. The lone pair are the little two electrons hanging out together, like a cute little couple of electrons, right? So bonds and lone pairs are domains. What about this kind of bond? Somebody tell me, if I have a bond that looks like this, is that, how many domains is that? How many domains is that? How many of you guys think it's 3 domains? Raise your hand if you think it's 3. Okay? Raise your hand if you think it's one domain. Okay, does somebody want to tell me why they think it? It's okay if you're wrong, you guys. I just want to know what you're thinking about. Yeah, Bethany.
I think it's one of them because, what we mentioned it. Because it's one domain where they're sharing it. So there's enough, so it follows the octet rule.
Okay, so it's one domain because they're both sharing it with each other?
Yes.
Okay. Leslie?
I think it's 3 because it says that it includes bonds and lone pairs, but there's only bonds. There's no lone pairs, and then there's 3 bonds.
Okay, so there's 3 bonds. Is it 3 bonds or is it a triple bond?
Triple.
It's a triple bond. That's one bond, but it's a really strong bond. It's a triple bond. This would be 3 bonds. 1, 2, 3. So that would be 3 different domains. But this is one bond. It's just a really strong bond. It's like holding on with like 3 arms, okay? It's just a really strong bond. So it's one bond. This is one domain, okay? So the shape of a molecule depends on the number of domains. So I want you guys to go ahead and tell me, we're gonna skip this one. Right here, I want you to circle the domains around the central atom only. So I don't want you to circle these ones over here because that's not the central atom. Carbon is the central atom. It has one domain. It's a double bond. One kind of bond. It's a double bond. One bond. It's just stronger because it's got 2 arms holding it. Okay? That's one domain. That's 2 domains. 1, 2. Okay? I want you to circle the domains around the central atom for all of these on your computer. Go ahead. You can actually draw on this slide. Alright, I'm gonna do it on the board here. Okay, so I'm gonna rewrite the central atoms for me. Okay? This should be the same for you guys on your screens. Okay, for this one here, my central atom is nitrogen. So I'm only going to be circling whatever's on nitrogen, the domains on nitrogen. Over here, iodine is my central. Oxygen over here, nitrogen again over here, and then sulfur over here. Okay? Domains. How many does this one have?
3.
3?
4.
1, 2, 3. Don't forget those 2 dots there. 4. How many does iodine have? 1, 2, 3, 4,
5.
1, 2, 3, 4, 5. I'm only circling the ones that are on iodine. So I don't count all these ones on chlorine. Because iodine is a central atom. Okay, this one, how many?
3.
Good. Be careful with that double bond. That's 3. Here, how many?
4.
Yes, 1, 2, 3, 4.
3.
Okay, 1, 2, and 3. Good. Part. Okay, cool. So now that we know the number of domains on the central atom, okay, we are going to be able to tell the shape of the atom based off of the number of domains. And not just the number of domains, how many of them are lone pairs and how many of them are bonds. So get your chart out, the chart that I gave you with all the different shapes. It looks like this. This one, I have extras in case you don't have it. I have extras, I'll give it to you. Okay. Alright, so if you see on your screen, this is exactly what you have on your sheet. Okay, so it tells you the different shapes of the molecules based on the number of domains. Okay, so the domains here, it says, if you have a total of 2 domains, how many of them are lone pairs?
0.
and then it tells you the shape. Okay? So if you have two domains, 0 lone pairs, it's going to be linear. So for example, here's an example of a molecule that looks like that. CO2. 2 O's. How many domains are around carbon? 2. So 1, 2. How many of them are lone pairs? Remember, a lone pair is when you have 2 little electrons like that. 0. There's no lone pairs around carbon. So 2 domains, none of them are lone pairs. It's linear. This is linear, which means it looks like this. It literally looks like a line. That's the shape of that molecule. If I were to make it out of all of those little pieces over there, it would look like that. What about, let's see, right here, if I have 3 domains, and one of them is a lone pair, okay? So for example, if I have, which one could that be? I'm not gonna do that one. Actually, I can do it. Okay. How about, actually I'll do this next example right here. 4 domains, and then 2 of them are lone pairs. So I'll do that one over here. Okay, so I have oxygen connected to a hydrogen and another hydrogen, and then it's got these lone pairs right here. How many domains around oxygen? Raise your hand. How many domains around oxygen? Melanie, yeah. You raise your hand for a second, right? Go ahead, try it. 3?
No, 2.
2? Which ones?
The one with H
This one?
and the other one.
2.
Or is one the 2 dots?
Don't forget these, so there's 4. How many out of 4 are lone pairs? 2 lone pairs, good. So, 4 domains, 2 lone pairs, what shape is that gonna be?
Bent.
Bent. This is gonna be bent. And so if I were to actually build that out of a model, it would look like this. It would look like it was bent, like that. That's oxygen, and those are the 2 little hydrogens. You see, like that? Because you don't really see the electrons when you're building a molecule like that. It just looks like this. Yes?
What do you mean by lone?
Lone pairs, good question. What do I mean by lone pairs? Andrea, what is a lone pair?
It's when 2 valence electrons, like those 2 that are on the top of the hole, they don't have a bond.
Yeah, they're not bonded to anything. They're just hanging out together like a little, like a couple, like best friends. You know, like when you're in the hallway with your best friend, you know? Okay. So, for example, if I have nitrogen like this, and I have hydrogen connected all around, and then 2 little dots up here, that's a lone pair. Good. Oh, the moment of realization. Okay? So, that's how you figure out what shape it's gonna be. All right. Let's see. You guys are a partnership. You guys are partners. You're- Actually, wait, 2 to 4. I think there needs to be somebody who's alone.
Oh,
You wanna be alone?
yeah.
Okay. All right. So you 2 are gonna be partners, and you 2 are gonna be partners. Go ahead. Okay. All right. Go ahead and sit next to your partners that I just assigned you. Go ahead. Close your computers. You don't need them anymore. Have your charts out, and I'm gonna pass you your packet and your little Ziploc.
I can completely turn.
Here we go. So everyone should have a packet. Everyone has a packet. Yes. All right. You're gonna spend the next 30 minutes on this. This is gonna be your homework. Okay. So in the front you have a little introduction. This introduction tells you what a covalent bond is, what Vesper theory is, what Vesper stands for. It tells you why molecular shape is super important in science and in the world, really with your body. It affects how you taste things, how you smell, the way that you can see. Molecular shape, the geometry of it, is super, super important for all life. Okay? This paragraph, these 2 paragraphs tell you a little bit more. And then you have questions on the bottom. Okay? I want you to go ahead and skip those questions for now. You can answer those for homework. So go ahead and flip the page. You have a table. This table is what you're going to fill out. At the top, it says purpose. You're going to build 3D models of covalent molecules. Okay? You have a baggie full of pieces. Each piece is a specific atom. Okay? So it says black is carbon, white is hydrogen, red is oxygen, blue nitrogen, green, orange, and purple. Any of those colors could be chlorine or fluorine. Okay? All the little gray sticks are gonna be how you bond them together. Okay? Notice, everyone take out the black carbon. How many holes does the black carbon have on it? Four. Where's you guys, there should have been 4 baggies. Where's the 4th bag? Okay, it has 4. Just like how carbon has 4 places that it can have a bond. Okay, so those little small holes where you can connect, that's where a bond can go. Okay, how many does the blue have? 3. That one's nitrogen because nitrogen only has 3 spots. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. Those are the 3 spots where it can have a bond. Okay? So those little holes tell you how many bonds it can make. So, follow the steps. It says, obtain a molecular modeling set. I already gave that to you. Study the color code. I already showed that to you at the top. Okay, number 2, one person in your group create a model that is in your table.
Okay, so for this one, it says that it says electron groups, but it only goes up to 2, but this one says 1.
Okay, the reason why these are weird, is your pencil? The reason why these are weird is because usually in your chart, they have one central one and then everything around it, right? But this is just 2 of them connected to each other like that. So this one's gonna be weird. Whenever it's just 2 connected like this, it's always gonna be linear. Always. Okay? Ladies, so someone brought up a really good point. Everyone has their chart, right? We're gonna add to the chart. So take your chart outside of your sheet protector because we're gonna add to it. Okay. If you notice, your chart shows you molecules that have a central atom in the middle and other atoms bonded to that central atom, right? Doesn't all of your the molecules on there look like this, or it has a central atom and it looks like this? Yeah. There's always something in the middle? Yeah. Whenever you have a molecule where it's just 2 atoms bonded to each other, like this, and there's nothing in the middle, for example, the hydrogen that we just did. Another example that you have on there is chlorine, that looks like this. You see how it's just 2 connected to each other? Yeah. That will always be what shape? Linear. So I want you to put on the side of your chart somewhere, when you can literally draw this and then draw the examples like this. And then I want you to put always linear. Always linear. Okay? Draw this on the side somewhere. Okay? Alright, keep going after you've done that. You can just keep working. You guys have about 10 minutes. Keep going. Oh, that's all.
For this one, it looks right here, the way it looks right here, it looks like it can't be symmetrical. But then, like, if you cut it like in half like this way or like this way.
Okay, so let's build it. That's the whole part of this activity. You're no one's building. Make sure you're building, you guys. You better build, because it will help you figure out if it's symmetrical or not. It's kind of hard to tell when it's on a flat piece of paper, but when you build it and see the 3D model, you can see if it's symmetrical, you can see the shape. Okay.
No.
Wait for it.
White.
No, pairs. Things that are getting connected. Your requirements
What if I cut it right down the middle, right here? It can, you can cut it even right here. Okay, so if you cut this in half, they would both look the same. They really would. I know it's kind of hard to tell because it's like at weird angles, but if I did this, it would be symmetrical.
Okay.
Okay? It would be different if it was like, if there was like a whole other you know, like, but all of those are hydrogens. But this time, that's hydrogens.
But if you said there is like another molecule, wouldn't it be the same because it's cut in half and they each have that part of the same?
What's the point of this?
But then it depends what's connected to that molecule. Okay? So, you'll see some other ones where they're not. Good question. Questions? Anyone need help?
I have a question.
Don't tell me, no, it's
No,
not
we
me.
just said because for this one, so there's not like, you can't put like the long pairs around it.
You're not doing long pairs for anyone. We're just doing
So
five.
then we just do this, wait, not that, not the third one, like that then?
Because in reality,
This one.
even if this had little lone pairs, you can't just put little dots. Electrons can't see little pairs, it's super small. So this is all you can see. And so don't worry about the lone pairs, just worry about the dots. No, yeah.
It has to be.
Okay.
Miss